we noticed in the previous few examples when we talked about the first derivative test, everything was about increasing, decreasing, relative max, relative min. There was no mention at all of concavity or inflection points. So we only talked about how the function was changing. We never talked about how the curvature of the function was going to be. And so I have students in the past who have said, well, Mr. Sylvain, if we use the first derivative test to find relative max and relative min in intervals of increasing and decreasing, is there something called the second derivative test, which will do the exact same thing, only with the second derivative, and tell us about concave up, concave down, so on and so forth? Well, the answer to the question is, there is a second derivative test, but it just tells us about the relative max or relative min again. There is another test which does, with the second derivative, the same thing that the first derivative test does with the first derivative. That's called the concavity test, and that's coming up shortly. But I did want to mention the second derivative test because it is a part of calculus, and you can absolutely use it on the AP Calculus AB exam. You won't be required to use it, but it's a nice part of calculus, so it's good to learn it. If and when you do take the AP Calculus BC exam, you will be required to use it on there. So with the second derivative test, here's the deal. The setup is basically the same. We want to find our critical numbers, and we do that by setting the derivative equal to 0. So let's say that we find out that the derivative is equal to 0. Okay. What we're at a particular point, which we'll call x equals c. Right? What the second derivative test says is take that value where the first derivative is equal to 0, take that value of x and plug it into the second derivative. And based off of your answer, you're going to find out whether you have a relative max or relative min. Okay. Now, why is that the case? All right. Well, let's look about it. Let's say that we're talking about a second derivative being positive. Okay. If the second derivative is positive, what does that tell us about the curvature of a function? Yeah, it tells us that the function is concave up, correct? All right, so let's have a concave up function here for a moment. Okay, there's a function which is concave up. All right, now we know that that function is concave up, and we know we're interested in the point, that value of x, where the derivative is equal to 0. All right, now the derivative is the slope of the tangent to the curve at a point along the way. All right, so we want the slope of the tangent line to be equal to 0. And if we're talking about a line that has a slope of 0, what kind of line is it? Exactly, it's a horizontal line. So we're looking for a horizontal tangent line. Where is the only point that I can draw a horizontal tangent line to this concave up function? Yeah, it's right here. That's the only spot on that concave up function where we have a horizontal tangent line. Where is that spot? That's at the bottom of the valley. That's at the relative min. So the second derivative test says that if the first derivative is equal to 0 for some value of x, and the second derivative is positive at that same value, then the function has a relative min at this value of x. So at x equals c. That's what you see in your notes right there. Okay. And if we flip this all around, we can determine when our function has a relative max. Why? Well, now we're still looking for a horizontal tangent line, but this time it has to occur with the function which is a second derivative is negative. What happens with the negative second derivative? We are concave down. And the only spot where there's a horizontal tangent line would be right there at the relative max. So if we have a value x equals c, in which the first derivative is equal to 0, and the second derivative is negative, then f has a relative max at x equals c. So just be careful with this, because a lot of times our brains like to think, oh, well, if concave up means positive, concave down means negative, and so therefore positive, that seems to be like a maximum value. So positive second derivative should be a relative max. That's not the case. It's a negative second derivative which produces the relative max. It's a positive second derivative which produces a relative min.